Okay, so welcome everybody for our first official talk of this workshop. We have Judy Miller from Georgetown University, and you're going to talk about adaptation and competition in a moment, Mark.
Thank you.
I'm looking forward to that.
So we have been talking a great deal about the speed of invasions, and I would like to focus for a while on what causes invasions to slow and stop, the ultimate extent of an invasion. From an evolutionary perspective, this is usually far from obvious. Take, for example, the tree line on a mountain. We look at the mountain, it's covered with trees up to a certain height, and then the trees stop. Why did that happen? Well, we could say that the environment too high up is inhospitable to the trees. But presumably the trees have been adapting to a changing environment as they climbed up the mountain. Why couldn't they adapt just a little bit more and advance just a little bit higher? So there are frequently such clear range boundaries in the absence of gross environmental discontinuities, and we'd like to understand why that happens. So the moment models that I will be going to introduce and talk about have their origin in an attempt to quantify the genetic swamping hypothesis for the setting of range limits. So the setup for genetic swamping is the following. We have a heterogeneous environment. Imagine an environmental gradient, like for example, a north-south climate gradient. And we have a population that is locally adapted or as it were, tries to adapt to the local environmental conditions. If we imagine that in the range center, there's a high population rate density, and at the margins, a low population density, then we can imagine that a constant influx of migrants from the center to the margins will be continually introducing maladapted individuals because they are adapted to the center where they came from, and inhibit adaptation of the population as a whole at the margins. So this was put forth as a verbal hypothesis by Haldane and by Meyer in the 50s and early 60s. And what got the trait moment models starting was a paper by Kirkpatrick and Barton in 1997 that quantified the genetic swamping hypothesis. So these are two theoretical population geneticists. They proposed a PDE model, which I'll display shortly. The dependent variables are population density, are M, and crucially, the mean of a quantitative trait, the mean of a continuous random variable like body size, or if we're adapting to climate, it could be the time of flowering in a plant and so forth. So we are looking at the difference between the mean value, the mean flowering time, say, and the optimal flowering time at that particular latitude, which would be determined by the availability of pollinators, presumably, and other things. In these models, the additive genetic variance is held constant. Additive genetic variance is the raw material for adaptation in a quantitative trait. If there is no variance of this type, then you cannot have evolution by natural selection. So here's the model of Kirkpatrick and Barton in their blockbuster paper that's been cited around 1,600 times. So there is a trait optimum which we envision as changing linearly in space, constant in time. Here are our population density and the difference Z between mean trait and trait optimum. Those are functions of space and time. We can see that if Z were absent from the model, we'd have Fisher KPP for M. Subtracting a half Z squared means that we are exacting a penalty both in intrinsic reproductive rate and carrying capacity for being away from the optimum trait mean. Then for Z, it's a little bit less intuitive why we have that particular equation. It derives from there, you can derive the equations by writing down equations for a full population density that has the trait and then taking its moments. It's mathematically difficult to treat largely because of that nx over n. Remember that we want n to be arbitrarily small at various places and times. So there are two non-dimensional parameters in the model. B essentially says how fast the optimum trait value changes in space. And A is essentially how capable the population is of adapting, very roughly speaking. We see that if it weren't for all this mess in between, we would have ZT equals negative AZ. And so the population would be approaching Z equals 0, which is the matching the trait mean to the optimum exactly. So Kirkpatrick and Barton didn't just propose this model, they simulated it numerically, and they discovered that for certain combinations of those parameters A and B, that when you start, when you initialize the model with a small founding population and then let it spread, it chops to a halt. This is a pinned state in terminology of nonlinear waves. And it is a natural formation of a range boundary from the biological interpretation point of view. Interestingly, and this makes, again, the equations difficult to analyze, what they discovered is that when we have these stationary pin states representing fixed range limits, the trait mean differential Z becomes unbounded. It grows linearly as space goes, as X goes to plus or minus infinity. So the theory of such equations has to be able to include such peculiar functions. There are also traveling waves. Kirkpatrick and Barton didn't focus much on those. A later paper by Garcia Ramos and Rodriguez looked into predicted wave speeds numerically for these equations. Okay. So since that model first appeared, all sorts of models have been proposed and studied mostly numerically that toss in various other environmental evolutionary population factors to see whether they promote unbounded range expansion, invasions, and inhibit range limit formation, or the reverse. So we are typically in continuous space. One important early paper that expanded this model was by Barton in 2001. In a book chapter, he extended the model to allow genetic variance itself to change as a function of X and T. There have been individual-based simulations. Dylan Morris and I were working on a sort of mating before COVID happened, and all sorts of funny things happened to people's research agendas. Here are more. Here are more factors that have been put in. That paper has, by my excellent former postdoc Farshad Shirani and myself, isn't in review anymore. I apologize. It came out in BMB last year. And so having a patchy habitat, discrete lumpy space, tends to pin invasions, as we would expect in the non-genetic model as well. Genetic drift, which reduces the efficacy of selection, inhibits invasions. It promotes range boundary formation. We have various kinds of stochasticity and various other shapes of environmental gradients other than just a linear change of environmental condition over space. So there is a large, at this point, hodgepodge of other moment models in which usually one factor at a time is added to the basic Kirkpatrick-Barton structure, and people discover what effect that has on sometimes invasion speed and more often on whether or not a stable range boundary forms. So the work that I would like to get to talking about confronts actually two potentially important factors in the same model. So in 2000, so just 3 years after the original Kirkpatrick-Barton paper, Case and Taper created and studied numerically a model for competition between two species that both were adapting to an environmental gradient. Their conclusion was that, for realistic parameter combinations, they disputed those, the parameter combinations that were deemed realistic by Kirkpatrick and Barton. For the common parameter ranges they deemed realistic, you could not get range boundary just from genetic swamping. You needed competition as well, which is a reasonable thing to test and not necessarily a surprising conclusion, since we know that competition is very frequently a key factor in setting boundaries between species domains. Not long after that, in his book chapter, when Barton added genetic variance as a dependent variable, oops, the genetic swamping and the range pinning went away, and he found, he concluded that if we allow the variance to vary, it will grow without bound, and eventually the population will burst out of any pin state it was in and invade and fill up the whole space. Now, that's a little odd, and maybe, well, that's a little odd because you would think that beyond a certain point, having a huge amount of phenotypic variance can't be promoting adaptation. Eventually, there will be just so much variance that very few individuals are near the optimal trait value. So, what Farshad did was to test these two predictions against each other by creating and studying a model that includes competition and adaptation and evolving variance. Okay. So this I actually have now said. So the model is a little bit complicated, but we see that there is a population density N, a population, a trait mean differential, he called it Q. Farshad is wonderful and also stubborn, and I couldn't make him change it to Z. and V for additive genetic variance. And they all evolve according to these reaction diffusion equations. There are a lot of parameters as well. And these, so there are quite a few parameters. A thorough literature search led us to reasonable ranges for those parameters. And here's what Farshad found numerically. So when we take out the competition, we have a model for a single species evolving along with its trait variance. For various reasons involving how the equations were derived, we reach what I think is a more reasonable model and outcome compared to Barton in 2001. There is no huge explosion and growth without bound of the trait variance. It has a global maximum and the variance decays as you get towards the range margins. Okay. So here we see the horizontal axis is the optimal trait gradient. So steeper climb in the environment is over at the right. And we see that what came out of these numerics is that wave speed declines at first steeply and then pretty much linearly along with the amplitude of the invasion wave until at a certain level it just becomes too much of an environmental climb and you no longer have invasion and they peter out at a small amplitude. So then we do competition and we get results that are broadly in line with what Case and Taper found in their model that held additive genetic variance constant. So two populations initialized at the same place end up partitioning the space between each other, and due to competition, the trait mean is further, for each one is further from the optimum that it would be if the species were evolving in isolation. There are more scenarios. So I would now switch back to argue that even for the original Kirkpatrick-Barton model, there is more complicated behavior to be found even numerically than what had been previously known. For example, you would think not surprisingly, but this hasn't been demonstrated yet in the literature, whether you get an invasion or a pinned range depends on your initial, can depend on your initial data. So here there's a very small initial inoculate founding population in a localized area, and the range gets pinned. Here, if we start with a wider initial distribution of the population, boom, it invades without bound. That, of course, sets the stage for hysteresis. So we are led to the prediction. Here, the time axis is going back, and the trait mean differential is going up. What was I? Oh, no, that's n. Excuse me. It's an n on its side, which looks like a z. So we are led to the prediction that if some event, be it environmental or what have you, takes an initially localized population and momentarily allows it to spread, it can happen that it will not, once the environmental conditions return to normal, shrink back to its original state. There's a ton of hard math problems associated with these equations. So regarding open questions, I'm happy to talk about the math, but don't want to do it right now. In the world of these moment models, I think that it would be useful to see more careful studies that include more than one complicating factor at a time. And that pay close attention to reasonable parameter ranges, because we have a lot of qualitative information about what happens when you add one complicating factor. And we see it speeds up invasions, it slows them down, it halts them. But models that toss in two, like, are quite rare, I think. And the last open question is a biological one. It's really hard to test the predictions of these models because of the difficulty of parameterizing them. In particular, how do you know what is the optimal trait value? You can't infer it from what the current trait mean is. Not only is that circular, but it would be wrong because in general, the prediction is that the trait mean is not at the optimum. So there is a great need for collaboration. I have a project going with a number of wonderful collaborators, mostly at Georgetown and an amazing recent graduate, studying the cabbage white butterfly in an effort to test the predictions of these moment models in a situation where there's a very close relationship between a certain climate-related trait and fitness, and in the hopes that we can use climate data to infer trait optima. That's going on. And I think I will just move to talking about this. Farshad did the heavy lifting on this paper. He is now at Georgia Tech. Niels Kairi worked with me on some other things. He was a PhD student of Vincent Calvez. Jackson Foran is an amazing person, an undergraduate. He graduated last month. Here are many biologists we are collaborating with. Former undergraduate assistants, former collaborator and hopefully future after COVID blows over, well, maybe not, and various other people who have been really great to talk to. Finally, this was funded both by NSF and some internal Georgetown grants, Claire Booth Luce, and hospitality from the Courant Institute while some of this work was being done. Thanks.